We're going to take a look at a specific tool or a particular tool to take a look at a second order differential equation and assume that we already have a solution to a second order differential equation, and then try to find the second solution for your differential equation. So this idea does come up a couple of times in our process of looking for the solutions to differential equations. But before we get started, let's try to remember what we did last time. And as a summary, here's kind of like what we did. We defined a fundamental set of solutions to be a linearly independent, a set of linearly independent functions that would solve or satisfy the differential equation. And we check for linear independence by using the Wronskian. If we have a homogeneous differential equation, that's a differential equation where it's set equal to 0, then we should be expecting, if we have a nth order linear homogeneous differential equation, we should be expecting n different functions that are linearly independent from each other. And the general solution would just be the linear combination of all those functions. If we have a non-homogeneous differential equation, higher nth order, and it's non-homogeneous, linear, then the solution would be the same as the homogeneous portion, but we're going to add on another solution that solves that particular differential equation, the non-homogeneous part of the differential equation. Now the y of p has to also be linearly independent from the rest of the other functions as well. Okay? So we're going to focus mainly on second order differential equations. We're going to get a couple of problems that would have the higher order differential equations, but our main focus will just be on second order. Okay? That's our summary. That's our long class from last time that was all abstract looking. So here we're going to take it a step farther, and this time we're going to assume that we only have one solution out of the two solutions that we're looking for. So we'll take a look at a second order linear differential equation, and we'll assume that we only have one solution. And we're going to try to look for the second solution by doing a substitution. Now the substitution that we're going to do is essentially going to be the first solution times another function. So we're going to rely on having one solution already, and then we're going to try to find another solution that's going to be linearly independent. And we're going to do that by taking our first solution that we already have and then multiplying that by another function. And then when we do that, we should have a differential equation with a u in it. And that differential equation is probably still going to be a second order differential equation, but you'll see that we're going to find a way to reduce that to a first order by doing yet another substitution. And we're going to solve for w. And then from there, we're going to come back and solve for u, and then go all the way back and solve for y. And hopefully we'll have two solutions. Okay, that's the idea. That's the plan. I'll do one example, and then you can try it and see if it works out for you. So the example, this is going to be a simple example, y double prime minus 4y is equal to 0. And we're going to assume that y1 is equal to e to the minus 2x. All right, so that's a good starting point. Yeah. Yes. Yeah, so we're trying to find out another solution because if there's a second order differential equation, we're going to need two solutions that are linearly independent. So how are we going to find the other solution? We're going to find it this way by assuming that another solution is going to look like the first solution times something else. Yeah. And then we're going to force it to be a solution, and somehow we're going to get to solve for u. And then once we solve for u, then we can solve for y, the other solution. Okay? So let's see. Our other solution should then be u times e to the 2x, right? So that's what y is equal to. And we need y prime, so we need to take a couple of derivatives here. So let's take a couple of derivatives, y prime, or we need y double prime. So a couple of derivatives. U is a function of x, and then we have e to the negative 2x. So we're going to need to use a product rule. Derivative of the first times the second plus the first times the derivative of the second. Wait, what? No, u is a variable. U is not just a variable, it's a function of x. Oh, okay. And then now we take the derivative again because we need the second derivative. So we need now we have two product rules. Derivative of the first times the second plus the first times derivative of the second. So that's the first part. And then the second part, we need to use the product rule again. Derivative of the first times the second plus the first times the derivative of the second, positive 4. It's probably worth simplifying this a little bit, right? To see before we put it back into our differential equation. So let's see. This is a u double prime e to the minus 2x. Let me collect all the u primes. There's two of them. Wait, what? Oh, this is a 2, yeah? Yeah, so that's negative 4. Yeah, minus 2x prime. And then the last one. Okay. So we'll put that into this differential equation. Oh man, what's going on? This big mess. U double prime e to the minus 2x minus 4 e to the minus 2x u prime plus 4 e to the minus 2x u. So that's y double prime. So this is the y, the regular y is just u e to the minus 2x. And that's it. It's equal to 0. Right? And then we see that there's some canceling going on here. So we just have u double prime e to the minus 2x minus 4 e to the minus 2x times u prime is equal to 0. So now we have a second order differential equation in u, but there's no u in here. There's just u prime and u double prime. So this is where we would want to make another substitution. And let's let w equal to u prime. All right, I'm having issues with my computer here. We can cancel it, and then you guys would be responsible for this. So what did I say? W. Maybe I should just type it all up. So u double prime is w prime, right? Can we solve for this? Now it's a first order differential equation. I think we can divide out by divide by negative or e to the negative 2x. So let's divide that out. And then I'll just get a w prime minus 4w. Is that right? 0. That's easy. Is it? Yeah, I hope so. dw dx equals minus 4u or 4w. It's linear, but it's also separable, right? Plus. Yeah, so w dw over w equals 4dx. So what's w equal to? Is it? Is it? Really? Did we forget? All right, I guess we have to do this slowly. Let's call it C1. What? Yeah. Well, no. Yeah, we have to go back. We have to go back 2 substitutions ago, right? So this is W, and we want to come back and find U. So this is what W is equal to, and we want to find U. So we know that U prime is equal to W, and then you need to find U, so we integrate. And what's the integral of this? There's all kinds of C1s and C2s popping out. Oh, this is U, not U prime. Yeah. Because U prime is W, and then so U is the integral of W. We're done. Now you go back to the first substitution, and this is really what we're looking for. So all right, I'm having issues with my computer. Y is equal to U times e to the minus 2x, right? And so this is equal to, what was U again, this big mess? C1 over 4. You can just call this one constant, right? 4x plus C2 equals. Oops, if I want to distribute this, we get 2x, right? Well, let's think about it first. We can think about this as our general solution, but the idea is that we have one solution already. We have one solution already, right? What we're looking for here is what your second solution is, a fundamental solution. Now this looks like it's a combination of a couple of functions, right? And if we take a look at this function over here, that's already our first function. So I don't think that function over here is going to contribute to our fundamental solution, right? In other words, if I take this y over here that we found, if I take this solution and I compare it to this solution, those two are not going to be linearly independent from each other. So y and y1 are not linearly independent. So they're, I could tell because I can write this y1 function as C1 times something, and then if I let C2 equal to, or if I let C1 equal to 0 and C2 equal to something, then I'm going to get this function again. So that function already exists in this y function that I just found. Say it again. This is y and y1. So what I want to do is I'm looking for fundamental solutions which means I don't really care about the constants. And at this point, I can let my constants be whatever they want, whatever I want them to be. And the thing is that this e to the negative 2 is already a solution that I have. So I'm going to let C1 equal to 0 and let C2 equal to, I don't know, just, it doesn't really matter what that constant is because my general solution will have arbitrary constants anyways. So I'll let C2 or C1 be 1/4 or 4. Yeah, we want C2 to be 0. Is that what I have? That thing that I wrote just disappeared. I don't know. Did I restart my computer? Maybe I didn't restart my computer. That whole thing disappeared. That was wrong anyways, right? Because I wanted C2 to be equal to 0 and C1 to be anything really. But if I let it equal to 4, then the coefficient will just be 1. So that my y2 is just going to be e to the 2x. Yeah, I let C2 equal to 0 because that part of the function is redundant. It's already in the other part of the function. I'm trying to find y2. And the thing is that my solution y has to be C1 times Y1 plus C2 times Y2. Now, if I included the C2 over here, then I'm just making things repeat itself, and so that's why it's not going to be linearly independent. So I just want the basic function that's going to make sense for me. So my general solution in this case is going to be y equals C1 times Y1, which is e to the negative 2x, plus C2 Y2, which is e to the positive 2x. Okay? YP in this case is there's no YP because a YP only would go with a non-homogeneous, and this is a homogeneous differential equation. Now, if this was a non-homogeneous differential equation, then we would have to try to find YP as well after this, because we still have to do this first. All right, how's that? Weird. Yes. If you have initial conditions, you can solve for C1 and C2. Say it again. Oh, just because I would make this a constant 1. Yeah. What I wanted to say is I just want to ignore this. I just want to ignore these things. Yeah. I want to get rid of the one with an e to the negative 2x because I know that that's already a solution, and I just want to get this other one. Yeah. Because linearly independent says that if I multiply this by something and then add it to this by something multiplied, a constant, and if I set that equal to 0, then the constants have to both be equal to 0. But the thing is that if I multiply this by 5 or something like that, and then I can multiply this by -5, and that would cancel out this part, and then it would be 0. So the idea is that one function is already within the other function, so I don't want to count that. Yeah. So out of the solution that we got, we're only going to pick, what's this? My computer's freaking out. I only wanted this part right here. Okay. Is that tough? It's a lot of steps. I think it's hard to talk about the steps because the steps are just this. First, you have a solution, and then you're going to let y equal to u times y1. And then you're going to put that into the differential equation. And then after you put it in a differential equation, you'll have something where you have u double prime and u prime. And then the u's should cancel. And then you're going to make another substitution. Is that worth putting into a step-by-step process? All right, so what are the steps? Okay, so take your solution, y1, and let a new y equal to u times y1. Okay? Yeah. Right. This is only going to work for second order. After that, we're going to substitute y into the differential equation. Yep. So make sure you use the product rule appropriately, correctly. And then you'll have a DE with y double prime and y prime. Yes, you, thank you. I don't know if that 3 was worth a step. Substitute w equal to y prime, right? Get a DE, get a first order with w. So sometimes it's separable, sometimes it's just regular first order. And since we're talking about linear differential equations here, we can either separate it or we can use the first order linear process. Okay. We're going to solve for W. Then we're going to go back and find U. By integrating W. Right? That's what we did. And then after we found that, we're gonna go back and look at your Y equals U times Y1 and eliminate any redundant terms. So this would be your second of your fundamental solutions. And then your general solution is going to be Y equals C1 times Y1 plus C2 times Y2. Okay. Wow. So I was going to try to derive the general formula in class so that we can just do a formula instead of going through this process. But that formula looked too complicated, so. Maybe you should try it. All right, so here's what I'm going to do. I'm going to put you guys in pairs. And I'm going to give you two problems. Okay. So whoever your partner is will be your partner, but you're actually not going to work with your partner. So between the two of you, you're going to get a problem, your partner is going to get another problem. And what you're going to do is you're going to split up. And you're going to find other people that have the same problem as you have, and you're going to work with them to solve your problem, because you guys will be working on the same problem. And then after that, you guys can get together with your partners again, and you can explain to your partner how to solve your differential equation.